Part 4, we're asked how large n has to be for a prime to fall between 3 and 4 with probability at least 99%. So this is just a slight variation on the problem we just did in Part 3. First of all, let's note that if I have a normal variable, and I'm interested in the condition that it falls within z standard deviations of its mean, with probability 99%, then by symmetry, the remaining 1% of the time is equally divided between falling above z standard deviations above the mean and below z standard deviations below the mean. So in particular, it has probability 99.5% of falling below z standard deviations above the mean. So we're interested in what z value has the property that the cumulative distribution function at z is 99.5%. So this is just a way of transforming the condition we're actually directly interested in to the sort of condition you would find in an old school standard normal distribution table. Like I keep saying, there's nothing special about phrasing the problem in this particular way. There's no particular reason we have to do this transformation, especially in the modern world with modern calculators, modern apps for this sort of thing. But if you wanted to look at an old style table, or if you only had access to, for whatever reason, the cumulative distribution function of a standard normal random variable on your computer, this is the kind of transformation you would do. So let's go find out what z value has the property that a standard normal random variable falls below that value z with probability 99.5%. If we go look at a table, it's a little bit off the window here, we see that somewhere between 2.57 and 2.58 is the z value we're interested in. So let's just say approximately 2.57 is the value we're interested in. So now the question, remember, is we want a prime to fall between 3 and 4 99% of the time, which in other words means we want that 0.5 deviation from the center in the interval 3 and 4, its bounds are both 0.5 away from the center, we want this to be 2.57 times the standard deviation of a prime. We want to figure out what is the minimal n to ensure this. And recall, the standard deviation of a prime is going to be the standard deviation of a single die roll, 1.7, divided by the square root of the number of die rolls. So now we can just directly solve for n. I suppose we'll get square root n is 2.57 times 1.7 over 0.5. And so n has to be at least the square of that. And all of these are really inequalities. And we see that the smallest integer that works, if you just plug this into a calculator, will be 78. So we need that the number of die rolls is at least 78 for our use of the normal approximation to tell us that the average of all these die rolls falls between 3 and 4 with probability at least 99%.